Hello again, and welcome back to YCP Chemistry Labs, your Colleges of Pennsylvania's YouTube channel to help you get ready for lab each and every week. We're here again for week 2 of the General Chemistry 2 lab sequence now to discuss the Alka-Seltzer analysis lab. So this week's lab has a goal to try to use gas laws to determine the amount of sodium bicarbonate or sodium hydrogen carbonate, two names for this chemical, NaHCO3, to determine the amount of that in a standard capsule or tablet, of Alka-Seltzer, or a generic version of it, I think in the case of lab this particular week. So we're going to use two gas laws to accomplish that task. Hopefully you've seen both of these in lecture by now. They are the ideal gas law, which ties together the four main properties that describe any sample of a gas: the pressure, volume, amount, and temperature. PV equals nRT, where R is called the ideal or universal gas constant and has a value of 0.08206 atmosphere liters per mole Kelvin. That number and those units are particularly important as they will sort of guide what we have to do with some of our data later on in the laboratory. The other gas law that we'll need to make use of in today's work is Dalton's law of partial pressure, which tells us that the pressure of any mixture of gases, so the total pressure exerted by that mixture, is simply the sum of the individual, or what we call partial pressures, the individual pressures, because they're now part of a larger mixture. And it's as simple as adding together those individual parts to arrive at the total. Although we'll use this law in reverse, because we will know the total pressure of our gas mixture and one of the parts, which will allow us to define or find the other part in the work of today's lab. And that's actually where your calculations will begin, and then you'll work into the ideal gas law. So the way that we're going to analyze our Alka-Seltzer is by reacting the Alka-Seltzer with acid. This will cause the creation of carbon dioxide gas, which we will collect. Then we'll have our gas, which we can apply the gas laws to, and from there work backwards using chemical stoichiometry, knowing what the balanced equation was for the reaction between the Alka-Seltzer and the acid. We'll be able to figure out how much sodium bicarbonate was present that generated the gas that we collected. We're going to use a setup, let me wheel it in, that looks a little bit like this. You'll have really a two-part apparatus to work with here. You're going to have a gas burette. You've used a burette before doing titrations in your Chemistry 1 courses. And this is a little bit different. It's calibrated or has the scale on it like your burette, but it looks like it's upside down and it's closed at the top. This is called a gas burette because gas is bubbled into it and rises to the top, so you need the top to be closed to capture the gas, and the scale reads from the top down because that's where your gas is, up here at the top. To get the gas in here, we will have our reaction in a flask over here that I have clamped into just a regular utility clamp on my stand. We will place some acid into the flask, our hydrochloric acid, and into that we'll use a little trick. We're going to use a gel capsule, just like maybe you've had medicine in a capsule like this. Maybe they're not quite as common anymore. But this gel capsule, if I come back to the board for a second, is just two separate hemispheres, essentially, all right, that are linked together. And we can open the gel capsule up, place some of the Alka-Seltzer inside it, and close it back up again. We'll want to put about 0.25 grams of Alka-Seltzer into the capsule before we close it up. All right? So we want to weigh the capsule empty Then we want to add Alka-Seltzer to it such that the amount of Alka-Seltzer is 0.25 grams. We've done some of the work on the faculty side of this and figured out that 0.25 grams of Alka-Seltzer is the right amount to fill this burette with a little bit of air on either side so that you won't have a really small volume and you won't go past the scale. It's a big problem if you go past the scale because then you have no way of measuring how much gas you've actually produced. So you'll put your acid into your flask. You will put some Alka-Seltzer into one of your gel capsules, drop it into your flask, and then you'll insert this gas delivery tube. Now this tube's one of the trickiest parts of the lab to work with. You need to get the other end of the tube into your burette. This is where you're going to get wet in lab. So if I was in lab, I would be taking off my wedding ring, my watch, and I would probably roll up my sleeves because this 2-liter soda bottle that you could see here is going to be filled about to this mark where my finger is with liquid, with water. And so I would go ahead and put the tip down and slide it carefully up into the gas burette, and then I can readjust everything. I can slide this up and down to get everything nice and settled and comfy. All right? And your hands are definitely going to be in there, so be prepared to get a little bit wet. All right? You will run 3 trials of your Alka-Seltzer reaction, hopefully getting a nice consistent set of data. But you'll use this same setup, just plunk a new capsule in each and every time. All right? Let me wheel this back out of the way and I'll go over the pre-lab exercises for you. All right, so there are 3 pre-lab questions today using the different gas laws that we might find ourselves using as part of the calculations for this experiment. The first question asks you to calculate the volume of a sample of carbon dioxide gas that's collected at 21.2 degrees Celsius and 752 torr. So there are a few different gas laws that involve volume and some of these other variables, but the one that connects all the properties of pressure, volume, amount, usually quantified in moles, not in mass, is the ideal gas law, PV equals nRT. Moles, of course, though, is a very important concept to us in chemistry, and it's connected to mass. Moles is essentially the mass of an object divided by its molar mass. So the small lowercase m divided by the capital M. I can substitute that in for n and arrange this as PV equals little m over capital M RT. And this equation can now be solved for the volume. The volume of your sample would be its mass times R and T divided by pressure and molar mass. One important consideration before you rush into substituting your numbers is to make sure that your units match the set of units that R has. Atmosphere, liters, moles, and kelvins. So you can see that your pressure needs to be converted from torr to atmosphere. Your volume needs to be converted, that's what you're going to find is the volume. Your temperature needs to be converted from Celsius to Kelvin. Your mass needs to be converted from milligrams to grams so that it matches the grams per mole value of your molar mass. So those are some of the unit conversions you'll need to do before you can substitute and solve for the volume. The second gas law that's involved in question number 2 is a little bit less involved or less extensive. Technically, we could tackle this one with what we'd call the combined or general gas law that says that for any sample of gas that has a constant amount, constant moles or mass, the 3 other variables, pressure, volume, and temperature, are related in this way. As they shift, as one shifts, say the pressure, the other 2 variables adjust as well. But in this problem, there's no mention of temperature, and the temperature is held constant. So that simply would drop out. That would be a T2 there. So we're left to solve for the new pressure, P2, when the volume changes from this larger amount to a smaller amount. So P2 would equal, we would just divide V2, so we'd have P1 V1 over V2. And here we have no worry about unit conversions because the two volumes are in the same unit set, so their units will cancel out. And our pressure can just stay in torr because we aren't working with R, the ideal gas constant here, and there's been no request to give the answer in a certain unit set. So you can go right ahead into that formula there. In the third problem, we're asking to really help identify an unknown gas. What's its molar mass? And we're again given the different other parameters. Well, just like we did up here in number 1, we can use the variation of the ideal gas law that has mass over molar mass substituted in for moles. So I've jumped right to this formula here. And solve this for the molar mass. So the molar mass, when you do your algebra here, multiply it to the left, divide the P and the V to the right, would be mass times R times T divided by P and V. And again, the qualifier that you want to use here is the units. You want to pay attention to the units, that you are matching everything with the units of R. So that's going to be your temperature, your pressure, your volume, and then the mass is going to be okay. Grams is fine. It's going to give you the grams per mole that your units should be for your final answer. All right. So those are some nice tips to get you started on your pre-lab exercises for today. So really nice experiment. A little frustrating at times, I'll be honest, because you're getting your hands into the water and getting the gas to transfer across through that tube. Sometimes it works a little bit better than others. So I'm just going to ask for your patience as you do this experiment. It is a fun little activity to see the gas generated and collected. But just be sure you're following the directions. You are putting your hands into an acidic solution, so if you have really sensitive skin, be aware that it might irritate it a little bit, and you'll want to wash off quickly after immersing your hands into the solution. Wearing gloves won't really help because in my experience your hands are submersed farther than the glove covers your hand. So your best bet is to get in there quickly, get your hands out, and get them washed off. Otherwise, there aren't too many safety hazards to be concerned with. Wear your safety glasses, of course, and follow your directions, and you should be set for a great experience this week. So good luck, and I'll see you in the next pre-lab video.